Hi there. So last time we saw some examples of applying the dichotomous search. Now we're going to draw on some of the results we have from bisection to look at the convergence rate of dichotomous search, i.e. the rate at which the error reduces to zero. The error being this difference between the numerical and the true solution. And that will motivate the next method in line search, which is called golden section search, which has a better rate of convergence. Okay, so last time we looked at this method called dichotomous search for finding the minimum along a line, a one-dimensional function, and it evolves around bisection. So bisecting and looking at either side. And today I want to move on to a related method called the golden section search, which turns out it accelerates the dichotomous search a little bit. And by doing this, having two types of methods, we've done this throughout, whether it be Jacobi or Gauss-Seidel or different ODE methods, we're sort of building up our understanding by comparison of different methods. So that's why it's there. So what we want to do finally is just do a brief convergence analysis of the dichotomous method, and that will give us a reference against which to compare the next method, which is called the golden section search, in terms of rate of convergence. So convergence of dichotomous. And we use the result from bisection, root finding, right at the beginning of the course. This is a nice bit where the beginning of this term's work connects with the end. That the error, and I'm going to call it E in this case because we've already used epsilon, okay? Sorry, not epsilon. It's clearer using this. The error evolves as E. So I is just our step here, by the way. 2i plus 1. I is just a step. In this case, okay, we have to get used to the different notation. B naught minus A naught. So that's our initial bracket, initial interval, and the error just halves approximately. Okay, there's a little epsilon in there, but approximately halves. I'm going to use that approximation at each step. I halves approximately at each step. And given epsilon is small, that's a very good approximation. But we have to do one more thing in order to compare the convergence with the next result, next method. So we want to this convergence is written in terms of step. But is the function calling, i.e. the function at c plus epsilon, c minus epsilon, that consumes computational effort, should we say computational time. So we really want to rewrite it in terms of number of function calls. So for each step, there are two function calls. I'm going to call m another integer. M is number of function calls. Yeah, of course, the reason we have two function calls is we're looking at C0 plus C plus epsilon and C minus epsilon. Those are the sort of each step. And it'd be important to know this because the next method tries to make an efficiency out of that sort of that bit of the algorithm. So we know that m equals to I, yeah, or I equals m on 2. So if we now rewrite our error law, which is I is 1 over 2, and then when we have I, we write this down m on 2 plus 1 times b0 minus a0. And we can then realize that we have a 2 to the power half there, so we have a square root of 2, so we can write this as 1 over root 2 the m b0 minus a0 on 2. We're taking out this 2 because this is your bisector, if you like. So initial bisector, so that makes sense of that. And then we have a reduction of error by 1 over root 2 per function call. And it turns out that the number of function calls each method is the best way of comparing efficiency. Okay, this will make more sense when we see the next method, and we can see where the function calls come in. But we have this result now that we have this factor of 1 over root 2. So basically, can we improve on this factor of 1 over root 2 that decreases the error? And the answer is yes. The method is called the golden section search. Oh, that's what I want to show you now. So let's and it's based on, if you've come across it before, the golden ratio. I'll define it as we go forward, but it's this sort of ratio that comes from ancient geometry all the way back to the Greeks, and we preserve this ratio from each step to the next. So let me just show you. So that's a dichotomous search. Then we quickly change, but a very similar diagram now, to the golden section search. Okay, so it looks similar. We're starting off at step I with a domain AI come BI, but now we've got rid of the bisector sort of explicitly. Instead we have a left and a right point. So the bisector is still there sort of implicitly, but we don't actually compute the bisector. So let me see if I can write it. So we have these 2 points, left and right, and these are symmetric about center. Okay, so that's first of all. So we've changed from C0 plus epsilon, C minus epsilon to now just a left point, x left and x right. And we haven't defined where they are yet. We're going to determine that. But it turns out that say if we're now selecting the left bracket, so the function of x left is less than x right, then we distribute the new points in a more in a different way from before. So basically, we make sure that the new right point, in this case, is the same as left one. So the saving you make about this is it means that if you've made a function evaluation already of f of x left, you already know it for the next stage. So you're going to hopefully reduce the number of function evaluations. But the way we do this is we're going to preserve ratios of sections from each step. So that's the other key aspect as before. So let me give an indication of how this ratio idea. So basically, the whole idea of golden section search is it preserves a ratio of sections. And there's several different ways of expressing this, but I'm going to do the one which I found most intuitively, which is I'm going to say let's make that distance in the first section A, and then the section there is B. So that's in this case is the ratio of the right point to the left point, sorry, of the right point to the whole domain is this one, and then we can find a similar ratio in the new section. Say when we're doing this, so we're going to call this C and D. And what we're all going to do is we're going to, because we preserve ratios, we're going to say let's let A over B equal C over D, and we're going to call that R. This is going to be related to 1 over the golden ratio. And this is we'll go into the algebra in a minute. But the idea is that by preserving this ratio, we're able to then have this nice inheritance of points between steps, and then we have the idea is that at each step we have only one new function call, because we've inherited the function call for x right, in this case, to the left. Obviously there's a symmetry with the opposite way around, the right ratio. Okay, so we've only had one new function called each time, and it's all because we can preserve, basically because we want to preserve this ratio of this section here to this section, C to D, A to B, means that we can keep on at each step ensuring that you just have one new function call. Okay, so it's this geometric side of it that needs to be sort of digested, and then the algebra flows quite nicely from it. So the question is, if we want to preserve these ratios of sections and make just one new function, is what is R? And that's what we're going to determine on the board now. So let's just sketch by hand that first section. Okay, so we had AI and BI, and we had XI subscript I left, XI subscript right, and I had this ratio here of A and B. Okay. So this is all in the notes. So A on B is simply XI right minus AI on the full domain, which is BI minus AI. And I'm in the lecture notes, I call this RI. You can do this whole derivation without the subscript I on R. It just, someone pointed out to me, a colleague, that this derivation was to determine what R is. So we want to allow it to be whatever you like, but it's going to end up to be a constant R in the end. So you want to allow that flexibility in the derivation. So it's up to you really whether you use Ri or R at this stage. But I guess it's slightly more specific if you use the subscript I here. And so that's the first bit that you have. So this is just for the case where we select the left bracket, and you can repeat it with the right bracket case, and it's exactly, you get the same result, but we're just doing it for the first case. And remember the new section then, we ensured that B I plus 1, the new B, is the same as xi right. And then the xi that is xi plus 1 right goes there. Then you just introduce a new point, which is xi plus 1 left. So we have that xi right minus ai on bi minus ai from the previous slide. Sorry, I'm not writing my superscripts properly there. Equals basically equals C divided by D. Okay, it's easier if you just draw it on the diagram. So it's C on D, but C on D is actually xi left, because those 2 points are in common. Divided by D, which is simply xi right minus ai. Okay, so again, we're presuming this ratio is C on D. It's not so neat on this thing, but it was neater on the board before. And basically in the lecture notes, you have the nicely sort of typeset diagram for the golden section search, and I recommend you sort of draw on these ratios just to get a feel for how it works. So C on D is xi left minus ai, which we have here, because that's in common, and D is simply xi right minus ai. So the way we get deriving R now is we now need to substitute expressions for xi left and xi right. And I've just got enough time to write down those expressions, and then I'll continue this derivation in the next video. So let's just do xi right a minute. ai bi right. So xi right is, so, and a way of thinking about R again is a ratio that when R is 1, x right is all over this side, it's bi. When it's over the other side, it's 1 over a. So we can think of it as a sort of weighting, a linear weighting or linear combination of your A's and I's and BI's. So remember, so if this ratio, which is the ratio of this small section to the large section, if it was 1, which is never going to be, but just imagine it could be 1, then xi right would be all the way over here. When it was 0, xi right would be in the middle. So you've got a linear combination of the two. And then conversely, xi left is kind of the other way around. There's other ways of explaining this, but this is the way I find most helpful. So basically these are linear combinations of A, I and BI weighted by RI. Okay, so those are the two steps. We've set up our expression for a ratio in terms of preserving this ratio A to B, small section to large section. And then we've got the expressions for xi and left, x and right. You can substitute them in, and then you get a expression for r. Okay, so let's see how I'm doing for time. Yeah, so in interest of time, I'll stop, and we'll carry on with that then.